My name is James Ashley. I'm a planetary scientist and systems engineer at JPL. I'd like to talk to you about meteorites that we have been finding on the surface of Mars. These are unique rocks. Many of the scientists looking at these did not expect to find these rocks when we went to Mars with the Mars exploration rovers and with Curiosity. But they should not be confused with the rocks that have been excavated from the surface of Mars and brought back to Earth as meteorites, which you may have heard about. These are the so-called SNC or SNCC Association rocks. These are different. These are rocks that have been found on the surface of Mars that have landed there as meteorites. So we need something of a new term to describe these. I like the word exogenite. They are exogenic to the location in which they are found. So if I use that term from time to time, that is why. I'm going to be trying to move through this very quickly because I have a lot of images that I'd like to share with you. Every time we find one of these, we learn something new. It's an evolving discipline. It's a new discipline. And I'm hoping that it'll be new to some of you, although some of these rocks have been known about for many years. But it seems like every year or so we find more of them. The interesting thing about them, farther from being simple curiosities in the surface of Mars, is that they are useful as tools for planetary science studies, specifically to the surface of Mars and to Mars surface processes. Imagine a meteorite that lands in the Earth environment. It's going to alter, it's going to weather in a certain way. That same rock in the Mars environment will alter in a different way, a way that is diagnostic to the systems of Mars. So just running through this very quickly, these rocks provide complementary insights into chemical and physical surface alteration processes. We now have 24 confirmed and candidate meteorites on the surface of Mars. And the challenge for these scientifically is to try to identify and separate features on the surfaces of these rocks that result from atmospheric ablation during passage to the surface from those that are the result of post-fall weathering. Those are the ones we want to get at. And unfortunately, some of these features are actually kind of similar. So this talk is going to touch upon a number of the processes that we think we've identified, including oxidation or rusting of these irons, which is telling you something about water, and the stony meteorites, acidic corrosion, which again is telling you something about water in the locations where these things are found, and they're all found within a few degrees of the equator, all right? Keep that in mind. We'll also be looking at aeolian abrasion and the sculpting from sandblasting of the surfaces. And if there's time, I'll mention the topic of my poster tomorrow, which is the implications for astrobiology, because it turns out that the chondritic meteorites may actually be good places to look for first colonizers of microbes, and they're also very good at biosignature preservation, which might be worth considering in a sample return, okay? Now I'm going to pick up the pace and get away from the feedback at the speaker. So the rationale is that these are uniquely reactive witness samples to aqueous weathering processes, and that they also provide a unique suite of surfaces for those processes that are not characteristic of indigenous rocks, okay? Complementary insights. So they hold those paleoclimatic history insights for the locations in which they are found. That means near the equator, which are important controls for paleoclimatic models. And they provide witness throughout many epochs of Martian history, because after all, some of these landed last Tuesday, and others landed 4 billion years ago, right? We also have samples of the same materials, unweathered, curated in our terrestrial collections. So if you want to think of those as analogs, in a way they're sort of super analogs, right? You could compare a weathered material directly with an unweathered version of the same parent body. If you had an H ordinary chondrite, for example, an H5. Let's take a look at some of these. Again, they're found at all 3 rover locations. We have 24 finds, but of course, many of these are almost certainly paired. So the question becomes, how much pairing, how much lumping, how much splitting do you want to do to arrive at how many falls these objects actually represent? And I've color-coded them to represent a likely 9 or so individual falls. And here are some examples. These first 4 here, these are a bit washed out on the hyperwall for some reason, but these first 4 here are the Block Island iron meteorite, and I'm jumping around in time for a reason, because first I want to show you something about oxide production, rusting of the meteorites. This is Mackinac Island. This is Shelter Island, Elon Rua, and Ireland, all at the Opportunity landing site. These rocks, Lebanon A and B, are in Gale Crater at the Curiosity landing site, and at the Spirit landing site we found iron meteorites too. Note that these are all irons. Looking at how these things are going to alter in the presence of water, we know from studying Antarctic chondritic meteorites, Antarctica is a Mars analog environment, that even at sub-zero temperatures, you can get thin films of liquid water at the interface between the ice and the mineral surface that are sufficient for mobilizing cations and trace elements that would be capable of reprecipitating elsewhere to perform produce secondary alteration features. In this case, rust. The red that you see around these black metal grains in thin section is iron oxide, actually goethite and acogonite, possibly lepidocrosite, oxyhydroxides indicative of water exposure. So too, in the Martian environment, have we seen evidence of rust. Now, you can see the microscopic imager mosaic here on Block Island, which has been mapped like a geologic map to show the locations of an oxide coating, which is the red, bare metal surface is green, and notice the Wiedmannstaaten pattern here, clearly indicated as a result of either acidic corrosion or sandblasting from the wind, okay? You don't get this from atmospheric passage. That's a post-fall effect, and you can see that on some of the Gibeon samples in the display cases over here. The Wiedmannstaaten pattern is diagnostic of octahedrite meteorites, and this is a 1AB octahedrite meteorite. We've determined that. The only way to get this is post-fall from, like I say, windblown sand or corrosion, and to see it in a cross-cutting relationship with this coating, which we do, means that the coating also came post-fall. It's not a fusion crust. It is rust. We've been able to measure the height of that rust in comparison to the height, topographic highs of those Wiedmannstaaten plates in order to confirm this quantitatively using microscopic imager pairs, stereo pairs. And so now we understand that this rust is the result of water exposure, and also that it was recently formed. You can see in the case of this Elon Rua example that the sand grains in these hollows being moved by the wind is removing the rust. It means it's weak, it's soft, it's subject to erosion, and therefore it must have been formed recently. It may be an indicator of extreme obliquity cycling, this is 2 degrees from the Martian equator, or the result of migrating ripples. Notice the blueberries in these hollows of this large pit in the Block Island meteorite, indicating that ripples did indeed move over this. You can form microenvironments in the pore spaces within the subsurface sediments to produce enough water to cause this kind of rusting. So it's a big unsolved mystery right now. Is this coating the result of migrating ripples, or is it the result of obliquity cycling of the planet's axis? And that is something we're still trying to figure out. I want to zoom in on this right now. The skeletal protrusion of relic metal into this pit area. And we do that with the microscopic imager on the Opportunity rover, showing you, notice the scale, that's 1 centimeter up there, this relic metal protrusion, and its shadow down here. This is the result of acidic corrosion. It must be. And we've seen many examples of this on many of these meteorites, including the entire hollowing out of the Mackinac Island meteorite, leaving behind this webwork of relic metal. And how do you get that? Well, it's interesting. We don't even really understand some of these processes in the terrestrial environment, although we do see some very similar features on iron-nickel meteorites here. The theory is that when iron sulfide nodules, troilite, gets wet, it acidifies. You get sulfuric acid from that. And that acid can then enlarge the hollow in which the troilite nodule resides until the troilite is exhausted and the process ceases. That would very neatly explain, I think, some of what we're seeing here. Going back to the first meteorite ever identified on another planet, this is heat shield rock, so-called because it was found right next to the heat shield about a year after we landed, because we spent a lot of time in Eagle Crater when we first arrived. And I'll just zoom in on this little area here to show an example of sculpting, because that's the only way you can get this kind of sharp-edged crest between the local hollows. And we also see examples of Wiedmannschatten patterns there. But the best example of wind-blown sand sculpting is seen on the surface of Lebanon and Lebanon B at Gale Crater, where your first impression might conclude that these are regmaglyphs that are typical of some meteorites, but your second impression will be that these can't be regmaglyphs because they don't really look like classic regmaglyphs. You see a lot of very subtle flutings and cornices and hollows and differential erosion taking place here that are the result of some pretty complex processes that we're still trying to decipher. The two most recent finds at Gale Crater are these two meteorites found within 350 meters of each other, which might cause you to assume that they're related, but they're chemically different and they have different surface features, and so they're not related. They're separate falls. Mars is probably a meteorite graveyard, meaning that we can expect to find these things wherever we land. Here are examples of some of the stones that we've been finding, and I'm quickly running out of time here. So let me just show you quickly that we do have microscopic images of the stones that show similar kinds of scalloping, pitting, and deep incision and other features, and these have been discussed in a recent paper by Schroeder et al. In Nature Communications. This rock is the only example of the 24 that might actually be an ordinary chondrite, which on Earth comprises some 82% of the falls that we receive. There's a paucity of the ordinary chondrites. It has to do probably with a survivability bias, or perhaps in concert with a selection bias as we're coming across these things and identifying them. But I'm just going to end it here.